passing one around so that you can see one. But ultimately, it's lots of stacks of individual current loops. That's what a solenoid is. Lots of stacks of individual current loops. So drawing a solenoid, it looks kind of silly when you try to draw it on a board or something like that. But a solenoid would be drawn as, again, current loops. And obviously there's some physical properties of a solenoid that are probably obvious to me and hopefully obvious to you. Like a solenoid is going to have a length associated with it. So how long is your solenoid? There's clearly going to be either a radius or a diameter associated with the solenoid. And I think the number of loops probably is something that would be associated with a solenoid. These are properties of a solenoid, or at least physical structural sizes of a solenoid. A solenoid is one of the easiest and best ways to make a culminated uniform magnetic field. And they are used for dozens of things. So I want to talk about how you calculate the size of a magnetic field inside a solenoid using Ampere's law. This is going to be a very similar conversation to how we might have used Gauss's law to find the electric field near an infinite line of charge or around an infinite sheet of charge. A lot of the things we're going to do are very much the same. So to understand that, I'm going to take a moment and draw this a little differently, because one of the things that we have to do is we really have to get a cross-section of the wires so that we can get an idea for what the magnetic field looks like inside a single portion of a solenoid. This might take a little while for you to draw, but I would encourage you to take a little bit of time with this drawing. So if the solenoid picture we just had, I hope that you notice that your solenoid is just a bunch of coils. So because of that, I'm going to look at this and say that this represents one cutaway coil of wire. Now I know that one of the wires is a little bit offset because it's actually a spiral, but we're going to treat them that the wires are small enough, and that's why I'm passing this around for you to see that the wires are small enough that it's not a terribly wrong to think that it's a bunch of individual coils stacked on top of each other, especially if you look at the one that has the smaller bit of wire. You see why it's okay for us to kind of treat that as a bunch of just stacked coils? So that's how we're going to do our calculation. So what I'm going to do is I want to put enough of them together so that I can have kind of a bunch of them to talk a little bit about what having them stacked together really means. For you guys, this might mean, taking a little more time to draw it and being more careful. You guys who have some kind of electronic way of doing this, you might want to consider doing it this way so that you have enough of them where you get something useful to draw. So this is going to be my solenoid. Now, thinking real briefly that this comes from the idea of a spiral, and I'm going to draw the spiral again. And I'm trying to give it that 3D look by one wire looking as though it's tucked behind the other. Don't know how good a job I'm doing there, but I'm hoping. So I have one, the idea being that this part has current kind of coming out towards us because it's in front of the other wire. And this part has current going away from us because it's going behind our portion. Can you guys get the idea that that's what's happening here? This side coming out towards us and going into the wall here, behind coming out towards us, going into the wall here, behind coming out towards us. It's a spiral. So the whole thing is, and this part isn't critical, but it means that all of these have current coming out of the board towards us. Should have drawn the dot and the X before I copied it and duplicated everything, but hey, here we are. And then all of these will have current going into the board, and this represents our cutaway of our solenoid. wire I'm going to focus on for this particular example will be this wire right here. I'm looking at just this wire for a moment. That wire has a magnetic field that will be circular, like so. And we know that it's going to be circular, but also that it's going to kind of get weaker as we get further away. So the red circles represent the concentric circles that are the magnetic field around that one wire I've indicated in yellow. And using the right-hand rule, and noting that the current is coming out of the wall, the direction of that magnetic field is circular, like so. Alright, so again, using my right-hand rule, around this wire, the magnetic field must curve this way around the wire. Everything okay with that? Any question about that? So every single wire at the bottom is doing this. You all got that? Every single wire at the bottom is doing this. Now, at the same time, let's consider one of the reciprocating coils at the very top. So I'm going to look at, say, this one at the top, right there. One of the loops that's very much right above the loop on the bottom. It too is producing a magnetic field. And the magnetic field for that particular coil is circular about that coil. So I know, green and red. Good choices, Mr. Shelton. No, it's perfect for people who, can't see them. Now, the current is going into the board there, so when I use my right-hand rule, put my thumb into the board, these have a magnetic field that's going to be going clockwise around them. So their magnetic field, or each piece of magnetic field there, will have a portion of the magnetic field that's this way and this way. So this way and this way, this way and this way, and finally this way and this way. Oops. This way. Everybody follow that okay? So the thing I do want you to notice is that all of the contributions to the magnetic field on the outside are in opposition. So whether I look at the top or look at the bottom, these bits of magnetic field are opposed to each other. Do you see that? So there's very little, if any, magnetic field on the outside of a solenoid, because these two competing sets of magnetic fields cancel each other out. But on the inside of a solenoid, all of those pieces work together to form a generalized magnetic field that's all in the same direction. Do you guys see that okay? So one of the things that we say about solenoids, and this is going to be one of those things that might be a little bit hard for you to accept at the beginning, is that an ideal solenoid is very long compared with its diameter. this produces a collimated magnetic field inside the solenoid and very little to no magnetic field outside the solenoid. And it's just a product of this, not just the cancellation and the reinforcement, but the fact that every single loop is doing this. So this is a compounded factor occurring for every single wire loop. So that starts to create more and more current through the center that is collimated and in a straight line through the center of our solenoid. And that magnetic field kind of stretches out on the outside like that when you reach the edges. So we get edge effects around the outside of our solenoid. Everybody doing okay so far? This is also how a bar magnet works, but that's produced by something else happening inside the atom. This one, we're generating it from current. Now, with all of that, I want to now kind of get some of the distraction out of here, because I think we have an idea of what's happening, and I don't need to have all these circles and everything. And let's focus on how we use Ampere's law to figure out the strength of this magnetic field. So there is one thing I want to talk about with the solenoid and how industrial magnetic fields are produced. Because obviously, if you're trying to produce an industrial magnetic field and you want a very strong magnetic field, you'd have to crawl inside of this, this tunnel of wire. And we use magnetic fields quite a bit, especially in medical imaging. So if anybody's had an MRI, you probably know that it's in the letters MRI, magnetic is the first word. Magnetic resonant imaging is what it stands for. And so for this, we're going to assume a magnetic field exists inside the region of space where our where the coils are, and that the magnetic field on the outside is maybe not zero, but very close to zero. In a few minutes, we're going to talk a little bit about the shape of this magnetic field. But let's take a look at the standard idea for a solenoid's magnetic field. This requires that we come up with a Amperian loop. That's what this part of this equation is about, an Amperian loop. Now, an Amperian loop, like we said before, is a closed loop that begins somewhere around a current and comes back to that loop. So what I said to you is that we'll use a rectangle. And so let's do that again, a rectangle. And I'm going to put the rectangle in such a way that part of the rectangle is inside the solenoid and part of the rectangle is outside of the solenoid. And like I did yesterday, I will label the corners of the rectangle A, B, C, and D. And we're going to integrate along the loop. This is a line integral. That's what the B dot ds is about. It's a line integral, which means we are going to be looking for how much of the magnetic field is along the line of the rectangle. So starting from A, we're going to go along each side of the rectangle and try and calculate the amount of magnetic field that is in line with the direction of the rectangle we've drawn, the loop. So we're going to integrate in this direction. And although it may appear that the direction doesn't matter, it doesn't matter. It does matter a little bit because of the dot product that we're going to execute here. So this particular shape, because it's not a circle, suggests that we could take our integral and break it up into sections. Now, in all honesty, I should break it up in sections that are both inside and outside of the region of space where there's a magnetic field. So if I wanted to be super specific, I would consider integrating from here to here and then here to here separately, because there are separate parts to that. But it's all going to result in zero for that portion of the integration. So we'll talk about it, and we'll be really careful, and I'll be I'll be patient and in the way I explain it. But we're just going to treat it as one line integral from A to B. and then again from C to D. So again, first thing I want to do is take this and make sure I'm integrating over one complete path. So B dot ds from A to B plus B dot ds from B to C plus B dot ds from C to D plus B dot ds from D back to A. And these are all dot products. We're utilizing, we're purposely choosing this set of loops so that we can exaggerate the results of the dot product. Now, yesterday when we talked about this, we did this quickly, so let's hit the easy one first. There's no magnetic field here. So from B to C, even though there is a length there, in fact, I think we should probably come up with some values to use here. So I'm gonna call this lowercase l for the length of our rectangle. There is a length there, and we are integrating we're integrating, I guess, in the direction of our loop. So our dot product, I guess, could be considered to be 0, but doesn't really matter because there's no magnetic field. So because there's no magnetic field, that particular line integral from B to C is going to resolve to be 0. Now let's handle, I put it in the wrong spot. Let's put it in the right spot. There, from B to C. Now it's going to resolve to be 0. Now let's handle A to B for just a minute. And to handle A to B, consider that A to B actually needs to be sectioned off right here in the middle. This portion of that integral from here to here will be 0 because there's no magnetic field on the outside of this solenoid. So that one's easy. But the one that we need to pay attention to is this portion. From A to that halfway point, we are in a region of space that does have a magnetic field. But the magnetic field in that region of space is this direction. And the direction of ds is this direction. And we're going to be computing a dot product, and the dot product requires the cosine. And this is going to be the cosine of 90 degrees. So we'll also resolve a line integral here that will result in an integration that's 0. Because although there is a magnetic field in the region of space from A to the midpoint, the magnetic field and the direction of our integration are at 90 degrees. So that produces a cosine of 0. So applying that to both from A to B and C to D, we can get rid of both this integral and this integral, which leaves only one region left that we have to integrate, and that's from D back to A. Now, in going along the region from D to A, yes, because dot products are always cosine. So just a reminder that a cross product is sine and a dot product is sine. But more importantly, the principle of the dot product is how much of the magnetic field is in the direction of your line integral. So, here, are there any components of the magnetic field that are aligned with the direction of the Amperian loop? And from here to here, there's no component of the magnetic field that's in this direction. The magnetic field is perpendicular to that direction. So the dot product renders a cosine, but the angle between the magnetic field and ds is 90 degrees, and therefore it resolves to 0. Now, from D to A, that's not true. Our magnetic field is actually 100% in the direction of ds, because ds is going to be this way, and the magnetic field also this way. So when we look at that particular integration, D back to A, we're going to get B times ds times the cosine of 0 degrees, integrated from D to A. Now, no matter where we are inside this particular solenoid, I'll point out this particular location right here. I'm going to draw some dotted lines here. That magnetic field is going to be the same because we are staying the same distance away from the edge of the solenoid. So I would expect the magnetic field to be the same size all along that line. Now, if I had drawn my Amperian loop like this, well, that'd be different because the magnetic field is getting closer and closer to the inside edge. But I didn't draw it that way. I was careful to try and exploit some of the symmetry here and make sure I was using a rectangular shape. So if you're asked to do this on an exam, make sure that the rectangle that you draw has a portion of the rectangle outside the solenoid, a portion of the rectangle inside the solenoid, and make sure that the portion of the rectangle that is inside the solenoid stays parallel to the coils, because we're trying to exploit that symmetry. So it is not uncommon to be asked to draw an Amperian loop to calculate the magnetic field of a solenoid, and the expectation is that you understand that in order to draw that correctly, your Amperian loop needs to have a side that is parallel to the coils. And it doesn't really matter where you put it inside the solenoid, as long as it's parallel to the coils, as I've drawn mine. Everybody got it? Now, with that alone, the magnetic field shouldn't change over the course of that particular line integral. It becomes a constant, which means I take B outside of my integration, and all that I'm left with is adding up the length from D to A. So each piece is a small piece of length that's going to go from D to A. So when I add up that small piece of length, I will get the length of the rectangle. So this resolves to just be B times L. So this started as a line integral around the entire shape. We broke it up into 4 pieces, one for each side of the rectangle. We made a reasoned argument about why 3 of those contributions were 0, and 1 of those contributions was non-zero, and it was the product of a magnetic field times a distance. In an Amperian loop, you're always going to get a magnetic field times a distance on that side of the equation. Gauss's law, it was always an electric field times an area. This side is always a magnetic field times a length. Are we good to move on? Because there's one more thing we have to do. We have to deal with the other side now. The other side is mu naught times I enclosed. Now, I'm going to slide this upwards so we can kind of work from here. Mu naught is a constant. I enclosed represents how much current is enclosed. Now, every one of these coils of wire has the same current in it. Right? We're using one wire that we've wrapped around, so it's just a long spiral. But our Amperian loop is collecting these individual coils of wire. Now, my image has a specific number, but I think you could probably recognize that I want to make this generic. So I'm going to replace I enclosed with the current passing through the coil, individual coil, or the current in the wire, times N, the number of loops contained in my Amperian loop. All right, so I is going to represent the current in the wire, and capital N here represents the number of coils we've captured with our Amperian loop. When we did this for the loop of current, we only had one, so we didn't have to have an N there. We just had I there. But in this case, we have an N to represent the number of loops. Go ahead.
Is I in the entire wire or it's a single?
Well, it's only one wire.
Okay.
Remember, it's one wire that's been wrapped into a spiral. So this represents whatever, just like when you had your lab, and you had you had multiple loops, but there's only one current. Does that make sense? Okay. But I enclosed represents the total current passing through the Amperian loop. So what this represents is the current passing inside here. Does that make sense? And that's going to be the number of coils times the current in the wire. So all that's left now is to take this and solve it for the magnetic field, which isn't much, but we express it two different ways. So there's the basic way, which is mu naught I times N over L, or mu naught I times lowercase n. And I'll explain what both of them are supposed to be, but let's understand there's not much here. This version is clearly what we just did. This stands for a new character, and I'm going to be frank with you. Different books use different letters here, so don't read too much into this, and don't forget what the meaning is. This lowercase n is called the loop density, the number of loops per meter. So you can either hard express it. I have a solenoid that's 5 centimeters wide and has 100 loops. Or you can say, I have a solenoid that has a loop density of 100 turns per meter, or something similar. And they'll say it like that. They'll use the word turns instead of loops. It's not uncommon for that to happen. So loop and turn, both the same thing. So when you're reading problems, or you're been told I need to make a solenoid with a certain number of turns per meter, that's what they mean. Now, one of the things I hope you notice is that loop density plays a massive role in determining the size of the magnetic field. But regardless, mu naught is a very small number. Right? And it's in the denominator. It's in the numerator. Remember, every time we calculated the electric field, we had epsilon naught, which was also a very small number, but it was always in the denominator, if you'll recall. So it tended to be a thing that increased our number. But here, to get a magnetic field of any reasonable size, you have to have a very high loop density. And at the same time, you have to understand that the amount of current that you have plays a role here, but you have to be careful with current. Current generates a lot of heat, and if you're using a lot of current, you understand things start to get hot. Now, make sure we understand that this is worth committing to memory, the magnetic field of a solenoid. 3 things about magnetic fields I've suggested you commit to memory. The first is the magnetic field of an infinitely long wire. The second is the magnetic field at the center of a single current loop. And now third is the magnetic field of a solenoid. There are 3 things for electric fields I suggest you memorize, 3 things for magnetic fields I suggest you memorize.